Hello everyone. In our last video, we have preprocessed our dataset for pneumonia classification with X-ray Dicom images. The video link should be coming right over here. You can just click on it and go there. First watch that video, then come here. In this video, we will start our training process. But before we do that, I have changed this last bit of code a little bit. In this code over here, we are first splitting our dataset, our label CSV file that we have created previously, into 80-20 ratio. In this 80-20 ratio, the 80% of the dataset will be used for training and the 20% of the dataset will be used for validation. We have created one function where we are taking the output path as well as our data frame. After that, our code is exactly like before. Now let's start with our training process. In this video also, I am using the same notebook as we have created previously. So let's start with importing our libraries. So we will at first import Pytorch, which is the torch library. Then we will import torch vision. From torch vision, we can also import transform. So this transforms is used for transformation of our dataset. So at first we'll convert our dataset into tensor, then maybe we can rotate it, scale it, translate it, however we want. Okay. But we don't use this kind of augmentations in case of validation. Because of that, we will create two transforms. One is for training and another is for validation. Okay. So let's import now our TQDM. Now let's import NumPy. At the end, we will import matplotlib so that we can plot our images. So now we will create two variables to transform our images. One is for training data, another one is for validation data. So over here, we have the code for transforms. At first, we're converting our images into tensor. Then we are normalizing it. After that, in random affine, we are using two arguments. One is degrees and another one is for scale. In degrees, we are rotating it by 5 degrees. So minus 5 degree to plus 5 degree. After that, we are scaling our images. This random resized crop will crop our images randomly with 224 and 224 dimension. We will not use horizontal flip, vertical flip. We should not use this kind of augmentations in medical dataset because if you flip your X-ray images, then your heart and other organs which should be in your left side come into your right side, which is not something we want. For validation transforms, we will not use any kind of augmentations like this. Okay. We will just take the data, we'll convert it into tensor, and then we will normalize it. For normalization, I have taken this value as mean and this value as standard deviation. Okay, so let's run it. After this, we need to create our dataset. For that, we need dataset folder class from Torch Vision. So before we do that, we need to remember that our file is in NumPy format. So we need a way to load our files. Let's create the function called load file. Over here, we will pass the path. Now, let's call it channel 1. We will talk about in a second why we are doing it. np.load will pass the path. Now, we will load our file as float32. So, np.float32. Now, if you remember, we have stored our images as grayscale image. Okay, this has only one channel. When we start to train our model, be it Resnet 50, Efficient Net or Inception Net, they take 3 channels. Obviously, we can do it with one channel as well. Now, the problem over here is, if we train the model with one single channel instead of 3 channels, then we need to reinitialize the first layer so that it can take only one single channel. In this case, this will not be transfer learning. We will reinitialize all the weights. So we will be learning from the scratch only. Because of that, we will take this one channel and we will stack it one after another so that we can make it 3 channels and we can feed it into our neural network so that we can do the transfer learning process. So we will call this variable RGB like image and we will stack it np.stack channel 1. So let's take this one, comma. Now let's stack it with our channel dimension, which is -1. Now return our RGB like image. So now let's plot one single image so that we can see whether our code has worked or not. So here we are using this function to read this path, which is our NumPy file, and we will plot this image. Awesome, it has worked. So now let's create our train and validation dataset. So for train dataset, from torch vision dot datasets dot dataset folder, will pass the path, which is this path, and let me just remove this one. After this, we'll pass the loader, which is our load file function. Then we will pass the extensions that our file is going to be, which is .numpy. At the end, we will pass our transform function. Then transforms. We'll do the same thing for validation dataset, but instead of train dataset, it will be val dataset. Then we need to change this to val. Same thing over here, val transform. Okay. So our train dataset and validation dataset is created. Now let's plot few of those images and see how it has transformed our data. Let's paste it. Over here, we are plotting 4 images, 2 into 2, 4. And we are plotting our images randomly. So 0 to 21,000 because our train dataset has 21,000 images. So let's plot it, see what is the result. Okay. So over here, you can see that this is 0, the normal class, normal class, normal class, normal class. Okay. So let's run it again and see whether we can get any pneumonia class. Okay. So over here, this is one pneumonia class. So this is happening, guys, because in our dataset, there are 3 times more normal classes than the pneumonia class. So we need to figure out what to do about that later. Now we need to create our training loader and validation loader so that we can feed it into our training loop. So to do that, we'll first create our train loader, which will be torch.utils data.dataloader. In this, we'll pass our train dataset, batch size. So let's define our batch size. Let's define our batch size by 64. This will be train loader. So we also need to define the num workers, which will be 2 in my case. If you have more CPU and GPUs than me, then you can use a different number over here. Num workers. At the end, we will pass shuffle, which is equal to true, so that it shuffles our training dataset. Okay. It will be very similar for our validation dataset as well. For validation loader, we will do val loader. This will be val dataset. And the only thing that will be changed will be this shuffle equals to true, which will be false because we don't need to shuffle our validation dataset. Now we can create our model. So let's define our class, which is pneumonia model. This pneumonia model will inherit from nn module. Okay, nn.module. So let's define our init. Let's define our constructor. We'll pass this pneumonia model over here and self. Now our init method. Now let's define our model, which will be self.model torch vision models Resnet 34. For this dataset, we will train our Resnet 34 model. Retrained equal to true because we will do transfer learning. So we are fetching the weights as well. Now let's define our last layer, which will be model.fc, a fully connected layer. This will be torch.nn.linear in features equal to 5 and 2, and our out features will be 1 because we have 2 classes, so it will be either 0 or 1. If it is 1, then it will be pneumonia class. If it is 0, then it will be a normal class. Now let's just set bias equals to true. After that, we'll do something. Let's just define this over here. Feature map will be torch.nn.sequential. We will use list over here. Inside it, we will take self.model.children. I'll just explain what I'm doing over here. Okay? And do slave self. So what we are doing over here, we are fetching something called feature map from the second last layer of the network. What it will do, we will use this feature map to visualize exactly what our neural net has learned. In which part of our images our neural net is focusing. We'll use this to visualize our model's weight on our images. We'll see exactly how we are doing it in our next video. So now let's define our forward function. It will take two arguments. One is the self, another one is the x, which will be our data. Then we'll take our feature map that we have defined previously. In this feature map, we'll pass our images through it. Let's also define grade, which will be the output of our model. Self.model and x. Let's return these two things, grade and feature map. Now let's copy paste a code so that we can define our device. To train the model, we need the GPU. Otherwise, the model will take like 4 or 5 days, which should take around half an hour. Now let's just call our model, which will be our Pneumonia model. And we will put it into our device, which we have defined in our last cell, this one. Okay. So if it is Cuda, then it will go into Cuda, otherwise it will be CPU. Then we need to define our loss function. Because this is a binary classification, we will use binary cross entropy loss. Okay. Right there. Dot.in.bce with logic loss. We'll put this into device as well. This BCE loss takes some argument called positive weight. Inside the BCE loss, we can pass exactly how much weight we want to put inside our positive classes. Because if there is data imbalance, so in our case, we have around 3 times more data for normal classes than our positive classes. So because of that, we need to put tensor 3. We want to put 3 times as much weight on our positive classes than our negative classes. So in this way, our model will not overfit on our normal class. Okay. Now let's proceed. We should define our optimizer. Torch optim atom will pass our model parameters as well as our learning rate, which we are setting as -4. Now we will define our scheduler variable. So let's call our torch.optim lr scheduler or scheduler, whatever you want to call it, dot step learning rate. So what it does, it will take your optimizer as argument. It will take the step size. We'll just talk about it in a bit, and something called gamma, which I'm putting as 0.7. Okay. So over here, what we are doing, we are saying reduce our learning rate by this gamma function, means by 70% in every 5 epochs. Okay. So if you say over here 10, so it will reduce our learning rate by 70% after every 10 epochs. Okay. So over here, we will do 5. In every step size, reduce our learning rate by gamma. If after a certain epoch, your model is not learning, then even you can use it by building a logic with validation accuracy. So if the validation accuracy or the training accuracy is not increasing after few epochs, then you can implement this step learning rate as well. Okay. So now let's run it, and we are downloading the model. Torch NN has no attribute called sequential. Let's go sequential. This S should have been capital. Now it should work. Awesome.